So I have to start by thanking Miriam, Marcelo, and Aurelio, the organizers, for inviting me to give this talk. And it's a pleasure to be in the Brazilian Mathematical Colloquium. And surprisingly enough, it's my first Brazilian Mathematical Colloquium. I think I'm the only Brazilian mathematician who had never been to a colloquium before. So this is joint work with Patrícia Battistelli, who's here from Maringá, and Miriam Manuel from USP São Carlos, who's, I hope, is here as well, one of the organizers. And part of this was done in an exchange program between Portugal and Brazil. What is going on? So let's start. This is going to be, it's not very much about singularities, so I have to do some definitions to introduce the reversible maps. Then there's going to be some very elementary algebra, some simple dynamics, and hopefully lots of examples which is the only place where singularities are going to come into it. So let's start defining. So an involution is the germ of a diffeomorphism, that it is its own inverse. So composed with itself, so you get the identity. So I'm going to be talking all the time about involutions here. My first contact with this subject was about reversible vector fields, which are a generalization of a property that happens in conservative vector fields. And in that case, if you have a solution of the differential equation associated to the vector field, and you map it by an involution, then let's see the graph of this. What is going on? Oops. If you have this graph of a solution, then if you map it by the involution, the copy of it by the involution is also a solution, but it's going on the opposite orientation, okay? The generalization for discrete maps, which is what I'm going to talk about, is that if you have a map that goes from x to f of x, then the image of f of x by the map is mapped by f minus 1 into the copy of x by the involution, okay? And I thought in the beginning that this would be very similar to reversing symmetries of vector fields. It's totally different. It's a lot more algebraic, and it was a surprise to me to discover how different this thing was. So that we're also going to use the concept of a symmetry of a discrete dynamical system. My diffeomorphism is a discrete dynamical system. And a symmetry is simply an involution, in our case, that commutes with the system. So if you compose it before or after the map F, you get the same result, okay? So that's simple. But so I'll start with an example. I'll follow all the definitions with this same example. If I take this map, this simple linear map, so it's minus x minus y plus a shear term. So what it does, it takes this square here and maps it into this parallelogram here, okay? And here's the inverse of the map. So the reflection on the horizontal axis, on the vertical axis, sorry, changes the sign of the first coordinate, is a reversing symmetry of this map, okay? So that's a very simple example. It shows you if I reflect this square here and I map it by f, it's the same as mapping it by f first and by f minus 1 first and then reflecting afterwards. So if you have two reversing symmetries, there are involutions. If you compose them, you have a new involution. It's again an involution, but it's no longer a reversing symmetry. It's a full symmetry. That's why I need symmetries in this story. It's a full symmetry. You can see, because if you're doing f minus 1 and f minus 1 again, you get f, okay? So we can form a group of all the symmetries that's of f. Taking all the symmetries, you get a group. You can form the set of all the reversing symmetries of f. That's not a group, but the union of the two is a group. So that's why we're doing here, right? You're composing two reversing symmetries, you get a symmetry, not reversing. The union of the two is a group, and the reversing symmetries are a coset of this subgroup in the whole group. Okay, we're going to use this. So it's very simple algebra. Another concept that we're going to need is the fixed point set of a map germ, which is simply the set of points that the germ fixes, that are mapped into itself. And there is some leftover here of something. There is some folklore lemma saying that the set of fixed points of a symmetry, not a reversing symmetry, of a symmetry of a map germ is invariant under the map. Okay, we're going to see what happens about the fixed point set of a reversing symmetry. But first, we're going to see that once you have a reversing symmetry, you get another one for free. So if you have this involution, which is a reversing symmetry of your dynamical system F. Okay, I'm thinking of F as a dynamical system. And if you compose phi 1 with F, you get a new involution. That's also an involution that's easy to show. And, and I can write F as a composition of this phi 2 with phi 1 because it cancels. Okay. And it's also F, phi 2 is a new reversing symmetry of F. So given a map germ and a reversing symmetry, I get another reversing symmetry. And conversely, given two involutions, if I compose them, I get a map that has these two involutions as reversing symmetries. So given these three things, I only need, if I give you two, the third is automatic. Okay. And we say then that F corresponds to this pair of reversing symmetries. I'm going to be using this all the time. So back to our example, we had this map that mapped the square into a parallelogram. And we had a reversing symmetry, which was reflection on the vertical axis. Now we compose phi 1 with F, and we get this new phi 2 reversing symmetry, okay, which is a lot more, it's an evolution, but it's a more, less simple-minded evolution than just reflecting on the y-axis, okay? So we have this second symmetry here. Actually, once you get one reversing symmetry, a second reversing symmetry, if your map F is, if no power of F is the identity, so you iterate F and you never get to the identity. In that case, you get an infinite set of reversing symmetries. Not only you get one for free, you get an infinite set of them, of reversing symmetries, and also an infinite set of symmetries, but that's more trivial. The symmetries is rather trivial because a map is a symmetry of itself. Being a symmetry just means it commutes with the map. A map F commutes with all its powers. Well, powers here meaning composition of F with itself, okay? Not powers in the sense of polynomials. So F commutes with any powers of F, so any powers of F are symmetries. If I'm supposing that none of them is the identity, this set is infinite. Okay, so my set of symmetries is an infinite set. Now, the set of reversing symmetry, I told you, is a coset of this set. So it's also an infinite set. So I take my initial reversing symmetry phi1 and take cosets of this set, and I get an infinite set of reversing symmetry. Actually, I get two, because I get left cosets and right cosets, right? And I'm going to call them, we number them like this. Phi k is phi1 composed with fk minus 1, and phi k prime are the right cosets, fk minus 1 composed with f phi 1. They don't, usually they don't coincide. We're going to see. And defined this way, of course, if I write k equals 1 here, is phi 1 composed with f0, which is the identity, so it's phi 1. Phi 2 here is phi 1 composed with f, which is how I had defined phi 2, and the rest is, and phi 1 prime is also phi 1. So I get a whole lot of phi index k and phi index k prime, which I'm going to explore now to understand better the dynamics of f. Okay, so back to our example, the same example all the time. Here, the phi k's are these maps. They're all different, as you can see. And the phi k primes are all these maps. They're different from the phi k's, because here you get k minus 1, in here you get 1 minus k. Okay, so we get this enormous symmetry, reversing symmetry group. And the fixed point subspaces here I've drawn only, these are linear maps in my example, so the points of fixed point subspaces are, well, in R2 they are lines or a point or the origin. So the fixed point subspaces, I've only drawn half the line, right? This is the fixed point subspace of phi 3 prime. Of course, it has the continuation that way. And this is the fixed point subspace of 5 prime. And you have all these different lines fixed by these different maps. Okay. So let's start playing around with dynamics. You remember I told you the folklore lemma that a fixed point space. Sorry, I have to interrupt a little bit. We had a folklore lemma that a fixed point of a symmetry, a subspace of fixed points by a symmetry, was invariant under the map F. Now, here it's not like that. What happens is that F maps the fixed point subspace of phi 2k into the fixed point subspace of phi 2k minus 1. So it's phi 4, a fixed point subspace of phi 4 into phi 2 into phi 2 prime, phi 2 prime into phi 4 prime, and so on. So it decreases, it goes in even numbers and decreases in the phi's no prime, and then increases in the phi primes. And the same here for the odd indexes. It goes by the odd indexes, so it jumps to and maps decreasing in the index in the phi's with no prime, and increasing on the phi primes. Okay. Actually, let's go back here. So what I'm saying is that the fixed point subspace of this one, phi 7, is mapped into phi 5, fixed point space of phi 5, then into phi 3, then into phi 1, then phi 1 goes to phi 3 prime, and phi 3 prime goes to phi 5 prime, and so on. And this one goes to that one. So that's how the map F acts on this set of lines, okay? I didn't show the fixed point spaces for the even, because they're all the same as phi 2. All the even indexes, in this case, all the even indexes, phi's and 5 primes, fix the same subspace. Okay. A more subtle consequence of this is that if I have a point in a fixed point subspace of phi, and if after L iterations by F, the point comes back to the fixed point, this fixed point subspace, then this point is a periodic point. Actually, it's a periodic point of period 2L. If you after L iterates, you go back to the fixed point subspace. Doing L more iterates, you go back to X. Not only you come back to the same fixed point subspace, but you come back to X. The proof is very simple. It's just a direct calculation. It's not a surprise. You start with F minus L and end up with F of L. So looking here, if I, for instance, I had this, all the phi 2k's, phi's of even index had the same fixed point subspace, right? Now remember that if I have, for instance, the fixed point subspace of phi 4, it was mapped by F into the fixed point subspace of phi 2. So it's the same subspace. So if it repeats, after one iteration, in this case, it comes back. It has to come back because it's the same subspace. And F maps this subspace into itself. So after 2 iterations, L is 1 here. After 2 iterations, you have to come back to the same point. So what this is saying, what this is saying is that if I'm starting here on a fixed point subspace of phi 2, which is the horizontal axis, then all points here have period 2. Of course, with this map, this is rather a trivial observation, because this map on the horizontal axis acts as minus identity, just multiplies the horizontal axis by minus 1. But it illustrates, makes it clear that using the two theorems, the two results, we can show that there are points of period 2. And of course, if it's a more complicated map, we can do more than that. We can even we can complicate the story. Don't look at this, this is horrible. This is just saying that if a point is in the intersection of two fixed point subspaces, and if after L iterations it returns to the intersection, then it is a periodic point, right? Why do I want the intersection of two fixed point subspaces? Because I know that the F maps one fixed point subspace into another fixed point subspace, which in my first example was the same one, but it could be a different one, right? And conversely, if I start in a fixed point subspace and I have a periodic point, then it is in another fixed point subspace of another. So this point is in the intersection of the two, okay? Then you can play the same story with, this is with the phi's, this is the phi primes, and then phi's and phi primes, okay? We were very, very happy when we found this. This is surprising result that you get lots of periodic points and you get lots of information in periodic points. After we were very happy with that, we discovered that Devani had already done it, except that he had only looked at the case where my space had even dimension and the fixed point spaces had half the dimension of the space, which is natural because that's the more obvious generalization of a conservative system. But our result is valid in general. Any dimension doesn't need any restriction on the dimension of the domain or of the fixed point subspace, right? So there we have it. But there is an interesting consequence here. I wish I had this on the maybe I could, no. I had tried to do this on the iPad. I'll have to do it with the pointer. Let's see if you can see it. Suppose if I have a point here in phi 3 prime, you fix the phi 3 prime. Sorry, that's start in phi 5 prime. If I have a point here in fix of phi 5 prime, no, phi 3 prime. Oh, what a mess. If I have a point here, then F maps the primes into increasing ones. So if I have a point that starts here, its image is in here. Fix of phi 5 prime. And if I have a point in fix of phi 5 prime, I have its image in phi 7. So if I draw a little curve from here to here, from this point here to here, F is going to map this into a curve from this line to this line. Okay, so it maps this component, this chunk of space between 5 fix of 3 prime and fix of 5 prime. It maps this chunk of space into this chunk of space. Of course, it doesn't have to be exactly this chunk of space, could be the opposite one that I'm not drawing here, the continuation, right? Because these are lines that continue to the other side of the, I've only drawn half the line. So in general, this is always true whenever you have a fixed point subspace that has codimension 1 in the space. If you have two involutions that are reversing symmetries of a map and fix a set of codimension 1, then well, you have to work a little bit more than what I said, but basically by the reasoning I gave you, each one of these fixed point subspaces divides the whole space into two components. So if I take all the fixed point subspaces and take the union of them, this divides into chunks, lots of connected components, right? And what F does is to interchange these components, which was what I had tried to show you in the previous slide, right? One of these triangular regions is mapped into another triangular region, and it acts as a permutation of these regions. Okay, so let's look at more examples. So for the examples, well, I'm almost out of time, right? I'm going to use, let me see, I'm going to use a classification of linear involutions in the plane given by Solange Mancini, Miriam Manuel, and Marco Antonio Teixeira. So that's where the singularities come. So we're using that. And they classified pairs of involutions on Rn. In this case, I'm using R2. Pairs of these involutions up to change of coordinates. And you have to do the same change of coordinates in both evolutions, of course. So we use this to obtain automatically, that gives you a classification of reversible, linear reversible maps of the plane. So we went to this list they had and started doing everything that we knew, studying the dynamics of all the things in the list. So there are three cases. One case is when the group generated by the two involutions is abelian, and the other two are cases when it's not abelian. So the abelian case is rather trivial, because what happens is if the two commute, then they are equivalent to reflection on one axis and reflection on another axis. And F is minus the identity. So not very interesting dynamics. Everything has period 2 except the origin that has period 1. Okay. A more interesting case is when it's given by this pair of involutions. This F, phi 1 changes the sign of the first coordinate and adds the other two, and phi 2 changes the sign of the other coordinate. So F has this form, it's minus the identity, it's minus the identity 2 by 2, plus a nilpotent matrix. And that makes it easier to compute everything. So we computed all the phi k's and phi k primes, not a very difficult thing. Computed all the fixed point subspaces, lots of calculations, and here they are. So here are all the fixed point subspaces. Let me go back a little bit. The fixed point subspaces for the even indexes are all different, but the fixed point subspaces for the odd indexes are all the same. It's all the vertical axis, okay? So here are all the even ones, all the prime ones and the non-prime ones. Well, not all of them, 10, up to 10, or up to 8 in the phi primes, okay? And the dynamics goes like this. If I have a sector here between phi 2 and phi 4, what is going to happen? Phi 2 is going to be mapped, the fixed point subspace of phi 2 is going to be mapped to the fixed point subspace of phi 2 prime and the phi 4 into phi 2. So I'm going to have either this sector between phi 2 prime, fix of phi 2 prime and fix of phi 2, or this sector, okay? And actually, this sector is mapped into this sector here. If I take for another one between the phi 4 prime and phi 2 prime, so the fixed point subspace of phi 2 prime is going to the subspace of phi 4 prime, and that of phi 4 prime into phi 6 prime. So this chunk, this yellow chunk, is going to be mapped into the next chunk, but reversing here, minus the next chunk. And like that, so on and so forth. I can do it. I could paint the whole image here with different colors by getting what is mapped. This one is going to be mapped into that one. Oops, here, between these two, and this one into the next one, which is not even in the drawing. Okay. Another case, when another case is the case when I'm almost over time now, right? Another case is a class of maps that depend on a modal parameter t. It's okay. So depending, this T is the trace of the matrix of the map F, and you have these two involutions. Depending on the value of T, you get a different dynamical behavior, and of course, geometrical behavior. I computed the eigenvalues here, and you can see that the discriminant here in the computation of the eigenvalues depends, is T squared minus 4, so T equals plus or minus 2 is going to be a dividing, separating case. If the trace, the invariant is minus 2, is exactly the example that I used to do from the beginning, right? Remember the one that mapped the square into a parallelogram. So you have the fixed point subspaces here. The interesting case is when the trace is less than 2 in absolute value, because then the eigenvalues are not real, the eigenvalues of F. So they are a pair of conjugate eigenvalues of unit length. Okay. So in the convenient basis of R2, I can write F as a rotation of the angle theta, which is defined by this eigenvalue, right? And the phi k's and phi k primes are reflections in angles that depends on this theta. And they're fixed point subspaces. Okay, then you can compute them. Notice that they are sine of something, cosine of something, plus 0, 1. So they are in the circle of center 0, 1, radius 1, and they are sines and cosines of multiples of this angle theta, integer multiples of this angle theta. Now, it all depends if theta is a rational multiple of 2 pi or not. So here are they are in the coordinates on this basis of, that writes F as a rotation. You have I've drawn them for theta equals 2 pi over 5. You get this 5 invariant subspaces. One of them is just the vertical line. Okay, here they are. But what is not obvious is that, I mean, this F in this example that I've drawn, this F is a rotation by 2 pi over 5. So a rotation of a symmetry of a pentagon, right? Rotate 1/5 of a turn around the origin in these coordinates, of course. But it's not at all obvious that if I reflect, phi 2 is a reflection on this line here. Oops. Phi 2 is a reflection on this line here. If I rotate around the origin 1/5 of a turn, reflect and then reflect on this line, it's not obvious that for every point, this is the same as rotating backwards, reflecting first, and then rotating backwards 1/5 of a turn, which is what is saying that this is a reversing symmetry. Of course, if the angle is not an integer, a rational multiple of 2 pi, then we got a dense set of fixed point subspaces, and the dynamics is a bit messy. Okay, I think I'll stop here because I'm over time. I'll just do you a zoo of the other cases. The other cases are similar. We had fixed point subspaces like that accumulating on a fixed point subspace of F in this case, and here they accumulate on eigenvectors, eigenspaces of F. Okay, and finally you have this. So I suppose I'll stop here, and if you want more details, you can look at the paper that is in Journal of Mathematical Analysis and Applications. Thank you.